Let me ask you a question. What exactly is light? Take a moment and think about it. Maybe your first instinct is to say it's energy moving from one place to another. Or perhaps you imagine it as tiny particles zipping through space at unimaginable speeds. Or maybe, if you're a little more scientifically inclined, you describe it as an electromagnetic wave rippling through the vacuum of space. Here's the twist. Every single one of those descriptions is, in a sense, wrong. At best, they're incomplete, and at worst, they're deeply misleading in ways that can really keep you awake at night if you think them through carefully. I'm Leonard Susskind, and I've spent decades pondering light, decades. And I can tell you with absolute honesty, light is one of the strangest phenomena in the entire universe. Stranger than black holes, stranger than the Big Bang, and in some ways even stranger than quantum mechanics itself. Why? Because light is the thread that ties all of these cosmic mysteries together. So buckle up. We're about to strip away everything you think you know about light, piece by piece, and reconstruct it in a way that actually matches reality. Let's start with a common misconception. Most people assume that light moves, that it travels, that it takes time to journey from one point to another. After all, sunlight takes roughly 8 minutes to reach Earth, and light from distant stars can take millions of years. That seems obvious enough, right? Light moves. It takes time. It travels. But here's the mind-bending part. From the perspective of the light itself, none of that is true. Not even a little. In Einstein's theory of special relativity, there's a concept called proper time, the time experienced by an object as it travels through space-time. For us humans, proper time ticks steadily. We age, we have memories of the past, and we anticipate the future. Our proper time is measurable and very real. But a photon, a single particle of light, experiences zero proper time. None. The photon that left the sun 8 minutes ago arrives at your eye at the exact same moment it was emitted. From its perspective, emission and absorption are the same event. Think about that for a second. The light hitting your face from the sun has been traveling for 8 minutes according to your clock, but for that photon, there is no journey. There is no time. The sun and your eye, from the photon's viewpoint, are essentially the same place. It gets even stranger. Consider light traveling from the Andromeda galaxy 2.5 million light years away. By our clocks, it has taken 2.5 million years to reach us. But for each photon, not a single moment has passed. From the photon's perspective, Andromeda is right next door. There's no distance, no passage of time, no journey at all. It's not intuitive, and that's understandable. Our brains evolved to navigate a world moving far slower than light, where journeys take time. The universe, however, doesn't care about our intuitions. It obeys the mathematics, and the math is crystal clear. Photons do not experience time. So, does light move? In one sense, yes. We measure it, we observe it traveling, and we know it takes finite time to cross distances. But from the photon's own perspective, there is no motion, no passage of time, no here to their journey. It simply exists at both endpoints simultaneously. This is not some philosophical abstraction. It's a direct consequence of Einstein's special relativity, a theory tested and confirmed countless times. Time dilation, the slowing of clocks for moving objects, is observed routinely in particle accelerators, GPS satellites, and cosmic ray experiments. It's a fact of nature. Now let's tackle something that confuses almost everyone: the speed of light. We know it's roughly 300,000 kilometers per second, the ultimate cosmic speed limit. But here's the subtlety. That's only true in a vacuum. Exactly 299,792,458 meters per second. That number is so fundamental that the meter itself is defined in terms of it. The distance light travels in 1/299,792,458 of a second. Light defines our units of length. Yet, when light enters a medium, water, glass, air, it slows down. In water, it's about 75% of its vacuum speed. In glass, slower still. In exotic materials, physicists have slowed light to nearly walking pace. In 1999, Harvard researchers reduced it to 17 meters per second inside ultra-cold atoms. In 2013, physicists stored light completely in a crystal for an entire minute, freezing it in place like a fly in amber. Here's the key. Individual photons never slow down. Between atoms, they still travel at sea. What we perceive as slowing is actually a series of tiny absorptions and re-emissions. It's like driving on a highway filled with stoplights. Your car speeds along between intersections, but the average trip takes longer. Light behaves the same way. Even when slowed, the cosmic speed limit is never violated. Now, let's dive into something truly spectacular and a little counterintuitive. What happens when particles actually exceed the speed of light in a medium? Remember, the speed of light in a vacuum, c, is untouchable. But in a medium like water or glass, light effectively slows down because of those tiny absorption and re-emission delays we talked about. That opens the door for other particles, typically electrons, to temporarily move faster than the light in that same medium. And when they do, something visually stunning occurs. Cherenkov radiation. Cherenkov radiation is the optical equivalent of a sonic boom. Imagine an airplane breaking the sound barrier. It creates a shock wave, that loud boom. Similarly, when a charged particle zips through a medium faster than the local speed of light, it produces a cone of light radiating outward along its path. This glowing blue light is the same one you've probably seen surrounding nuclear reactor cores. It's not just beautiful, it's a direct, observable consequence of physics in action. But here's the important point. Nothing has broken the universal speed limit. These electrons are faster than light in water, yes, but still slower than light in a vacuum. The cosmic speed limit remains intact, which leads to a tantalizing question. Could anything actually travel faster than c, the ultimate speed limit in a vacuum? Theoretical physicists have speculated about tachyons, hypothetical particles that would always move faster than light. Tachyons would never slow down to light speed, just as we can't accelerate to it. Their mathematics is fascinating and bizarre. They would possess an imaginary mass, meaning mathematically their mass is the square root of a negative number. More disturbingly, tachyons could potentially carry information backward in time, challenging our understanding of causality. Most physicists today treat tachyons as mathematical curiosities rather than real objects. We've never observed them, and there are solid theoretical reasons to doubt their existence. Yet the very fact that the equations permit them offers a glimpse into the deeper structure of spacetime and the fundamental nature of the speed limit. Next, let's return to a question that has puzzled thinkers for centuries. What is light, really? You might answer instinctively, it's electromagnetic radiation, or it's made of photons. You might even mention wave-particle duality. And yes, light behaves like both a wave and a particle, but only if you set up the right experiment to reveal that aspect of it. Wave-particle duality is far stranger than most people realize. Consider history. In the 1600s, Isaac Newton argued that light was composed of tiny particles, which he called corpuscles. Meanwhile, Christian Huygens proposed that light was a wave propagating through some medium. For roughly 2 centuries, Newton's particle view dominated. But in the 1800s, experiments like Young's double-slit experiment demonstrated conclusively that light behaves like a wave. It interferes, it diffracts, it does all the things waves do. The consensus shifted. Light is a wave. Then, in the early 20th century, Albert Einstein turned everything upside down. In 1905, the same year he published Special Relativity, Einstein explained the photoelectric effect, where shining light on a metal surface ejects electrons. Classical wave theory couldn't account for a puzzling detail. Brighter light didn't increase the energy of ejected electrons. Higher frequency light did. Einstein's solution was revolutionary. He proposed that light consists of discrete packets of energy, which he called quanta. now known as photons. The energy of each photon is proportional to its frequency. This explained the photoelectric effect perfectly and reinstated the particle nature of light, at least in some contexts. So, light isn't simply a wave, and it isn't simply a particle. It's a quantum object, something beyond ordinary intuition. Experiments reveal different aspects of light depending on how we measure it. If you set up a wave-sensitive experiment, light behaves like a wave. If you set up a particle-sensitive experiment, it behaves like a particle. But here's the truly mind-bending part. If you perform the double-slit experiment with single photons, one at a time, you still see an interference pattern. How can one photon interfere with itself? The answer lies in the wave function. The photon's quantum state passes through both slits simultaneously, only collapsing to a definite position when measured on the screen. This is one of the strangest, most experimentally verified facts of physics, and it's still deeply mysterious even after nearly a century. And yet, the weirdness of light doesn't end there. Enter quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. You can create pairs of photons whose properties are intertwined in a quantum way. Measure the polarization of one photon, and the other, no matter how far away, instantly takes a complementary state. Before measurement, both are in a superposition. After measurement, the correlation is perfect. Einstein thought this implied hidden variables, pre-existing information determining outcomes. But in 1964, John Bell devised Bell's inequalities, and subsequent experiments, from Elaine Aspect's 1980s tests to modern experiments, confirmed that local hidden variables don't exist. Entanglement is real, and correlations are instantaneous. However, don't get too excited about faster-than-light messaging. Entanglement cannot transmit information instantaneously. Each measurement outcome is random. The correlations only become apparent when results are compared using ordinary, slower-than-light communication. The universe cleverly enforces the cosmic speed limit, even in the face of instantaneous quantum connections. Let's shift our focus now to something that seems simple, but is actually profoundly deep: the electromagnetic spectrum. When most people think of light, they picture the rainbow: red, orange, yellow, green, blue, violet. That narrow band is the visible spectrum, what our eyes can detect. But visible light is just a tiny fraction of the full electromagnetic spectrum, a ridiculously small fraction. The spectrum stretches from radio waves with wavelengths measured in meters or even kilometers, all the way up to gamma rays, with wavelengths smaller than an atom. Here's the striking insight. All of these, radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, are all light. They are all electromagnetic radiation, all composed of photons. The only difference is energy. A gamma ray photon carries millions of times more energy than a radio wave photon, but the physics governing both is identical. They both travel at sea in a vacuum, obey wave-particle duality, and interact with matter according to the same laws. So, the microwave heating your food, the radio signal streaming through your headphones, the X-ray shining through your teeth, they're all manifestations of light. This unified understanding of electromagnetic phenomena is one of the great intellectual achievements of physics. It was first hinted at in the 1860s by James Clerk Maxwell, who mathematically unified electricity and magnetism. Maxwell showed that changing electric fields create magnetic fields, and changing magnetic fields generate electric fields. These fields can propagate through space as waves, which we now know as light. When Maxwell calculated the speed of these waves, the number he obtained perfectly matched the measured speed of light. He hadn't set out to find the speed of light. It emerged naturally from the equations. This was the moment physics realized that light is electromagnetic radiation, not some mysterious separate entity. Yet even Maxwell didn't fully grasp the deeper significance. It took Albert Einstein, 50 years later, to see that the speed of light isn't just a property of electromagnetic waves. It's a fundamental property of spacetime itself. In special relativity, c is the speed limit of causality. It's the factor that links space and time into the unified fabric we call spacetime. Light happens to travel at that speed because photons are massless, but even if photons had a tiny mass, the speed limit itself, c, would remain. This subtle distinction is profound. C is not the speed of light in a vacuum in the sense of being a property of light. It's a property of the universe, a fundamental constant that shapes the structure of reality. Now, let's explore a truly tantalizing question. Why does light travel at exactly the speed it does? Why c? Why roughly 300,000 kilometers per second and not some other number? At first glance, it seems arbitrary, and in some ways it is. The value changes depending on the units you choose. In miles per second, it's about 186,000. In light years per year, it's exactly 1. So in that sense, the numeric value of c isn't as important as the dimensionless constants of nature, numbers that don't depend on units. One of the most famous is the fine structure constant, denoted by the Greek letter alpha. Alpha. This number combines the speed of light, Planck's constant, and the electron charge in a way that units cancel out, giving a pure number, approximately 1/137. Alpha determines the strength of electromagnetic interactions. It dictates how strongly light interacts with matter, how atoms are structured, how stars shine, even the chemistry that underpins life itself. Why it's 1/137 is one of the deepest mysteries of physics. If it were slightly different, say 1/100 or 1/200, the universe would look radically different. Atoms might not be stable. Stars might not shine. Life as we know it might be impossible. This is what physicists call a fine-tuning problem. Some theorists propose there may be a deeper theory explaining why constants like c and alpha have the values they do. Others suggest we live in a multiverse, one of countless universes where constants vary randomly. In this vast landscape, we just happen to exist in a universe where the numbers allow complexity and life to emerge. Leonard Susskind himself was part of developing the string theory landscape, which envisions an astronomical number of possible universes, each with different constants. It's controversial, but it offers a framework for thinking about why our universe's speed of light and other constants are just right. Regardless of multiverses or deeper theories, the speed of light in our universe remains one of the most precisely known and profoundly important numbers in science. 299,792,458 meters per second in a vacuum. It's more than a measurement. It's a cornerstone of physics, linking everything from electromagnetic waves to the geometry of spacetime, to the very possibility of causality itself. Finally, let's take a personal perspective. Imagine looking up at the night sky as a child. The light from distant stars isn't just photons. It's a time machine. Every photon reaching your eyes carries information from the past. The light from Betelgeuse, that reddish star in Orion, has traveled roughly 700 years before reaching us. You're seeing the star as it was centuries ago, not as it is today. It may have already gone supernova, and we won't know until the light from that event arrives. Light, in this sense, is our messenger from the cosmos, linking us to events across time and space. Now, let's dig even deeper into the nature of light, where it truly starts to defy our everyday intuitions. Light is not just a wave, and it is not just a particle. It's a quantum object, something that exists in ways our classical minds struggle to comprehend. When you set up an experiment to detect its wave-like properties, it behaves like a wave. When you set up an experiment to detect particle-like properties, it behaves like a particle. But, and here's the crucial point, the photon doesn't choose which way to behave. It simply reveals the aspect of itself that the experiment allows. Take the double-slit experiment, one of the most famous demonstrations of light's quantum strangeness. Shine a beam of light through two narrow slits, and it produces an interference pattern, just like waves in water would. Now, do the experiment with one photon at a time. Astonishingly, the interference pattern still emerges after many photons pass through. A single photon, in some sense, interferes with itself. How is that possible? The photon exists in a superposition, its wave function spreading through both slits simultaneously. Only when we measure its position on the screen does it collapse to a single point. This is not hypothetical. It has been confirmed in countless experiments over nearly a century. It is one of the strangest, most experimentally verified features of quantum mechanics. And it gets stranger still when we consider quantum entanglement, where photons become linked across vast distances. You can create a pair of entangled photons such that measuring the polarization of one instantly determines the polarization of the other, no matter how far apart they are. Before measurement, each photon exists in a superposition of states. The moment you measure one, the other state becomes definite instantaneously, even across the universe. Einstein called this spooky action at a distance because it defied his intuition about locality. Experiments beginning with John Bell's inequalities in 1964 and continuing through Elaine Aspect's groundbreaking tests in the 1980s to modern experiments have confirmed that entanglement is real. There are no hidden variables predetermining outcomes. The correlations are instantaneous and cannot be explained by any local mechanism. However, this does not allow faster-than-light communication. Each measurement is random. You can't control the outcome to send a message. The instantaneous correlations only become meaningful when compared through ordinary, slower-than-light channels. The universe protects the cosmic speed limit, even in the face of quantum weirdness. Now, here's where it becomes poetic. Light is not just particles and waves. It is a bridge across space and time. Consider photons traveling from stars and galaxies millions or even billions of light years away. From our perspective, these journeys take ages. But from the photon's own frame of reference, no time passes at all. It's as if the beginning and end of its journey are a single, simultaneous event. These photons carry information across the cosmos, linking distant events, stars, and galaxies to our present moment, yet without ever experiencing the passage of time themselves. This perspective transforms how we see the universe. Light is not merely a vehicle traveling through space. It is a thread woven into the fabric of spacetime, connecting past to present, near to far. Every photon is like a messenger that bypasses time, delivering a snapshot of the universe's history directly to us. When we observe starlight, we are literally looking back in time. The star as it exists today might be gone, exploded into a supernova, or changed in ways we cannot yet know. But the photon carries the story from centuries, millennia, or even millions of years ago. The beauty of light lies not only in its physics, but in the cosmic narrative it enables. It unites electromagnetism with the geometry of spacetime, classical physics with quantum mechanics, the microscopic with the cosmic. Every discovery we make about light reveals new connections, new symmetries, and new rules governing the universe. In many ways, light is the glue of reality. It allows us to observe, measure, and understand the universe while remaining profoundly mysterious itself. Even our simplest experiences, seeing a rainbow, turning on a lamp, feeling sunlight on our face, are encounters with this extraordinary phenomenon. Each photon striking your retina is the culmination of eons of cosmic history. Each carries a quantum story, an interaction with matter, a bridge across space and time, yet experiences none of the journey itself. Understanding light challenges everything we think we know about existence, about time, about motion, and about reality itself. And this is the part of physics that is both humbling and exhilarating. After decades of studying it, we still don't fully understand light. There are open questions, paradoxes, and mysteries that continue to challenge the brightest minds. But the more we explore, the more interconnected and beautiful the universe appears. Light is not just an object of study. It is the medium through which the universe communicates with us. It is at once ordinary and extraordinary, familiar yet fundamentally alien, simple in its presence, but infinite in its implications. Let's now expand on the full spectrum of light, which reveals the universe in ways our eyes alone could never perceive. When most people think of light, They imagine the rainbow, but visible light is just a sliver of the electromagnetic spectrum. Beyond the colors we see lies a vast continuum of electromagnetic waves. On the long wavelength end, we have radio waves, used for communication across cities and even planets. Slightly shorter are microwaves, which cook your food and carry satellite signals. Infrared waves are associated with heat, letting snakes sense their prey or cameras detect warm objects in the dark. On the other side of the spectrum, we find ultraviolet light, X-rays, and gamma rays, carrying enormous amounts of energy, capable of altering atoms and even ripping apart molecules. What unifies this diverse range of phenomena is their underlying physics. They are all photons, all quantum particles, and all obey the same fundamental laws. The only difference is energy and frequency. A gamma-ray photon packs millions or even billions of times more energy than a radio wave photon, yet they both travel at sea in a vacuum, and both exhibit wave-particle duality. This is a profound insight. Light is a single phenomenon, manifesting in different ways depending on its energy. It is nature's universal messenger, whether it's warming your hand, powering your solar panels, or revealing distant supernovae. Historically, this understanding came together through the work of James Clerk Maxwell in the 1860s. Maxwell showed that electricity and magnetism are deeply interconnected. Changing electric fields generate magnetic fields, and changing magnetic fields produce electric fields. These interactions can propagate through space as waves, electromagnetic waves. When Maxwell calculated their speed, he found a number that perfectly matched the measured speed of light. This wasn't a coincidence. Suddenly, light was understood as an electromagnetic wave. Maxwell didn't just unify electricity and magnetism. He unified light with the very structure of the electromagnetic universe. Yet Maxwell's equations, as brilliant as they were, left deeper questions unanswered. They described how light propagates, but didn't explain why it travels at that particular speed, why the universe enforces a maximum, or why photons are massless. It wasn't until Einstein's special relativity, 50 years later, that the true significance of the speed of light became clear. C is not merely the speed of an electromagnetic wave. It is the speed at which causality itself propagates through spacetime. It's the universal conversion factor between space and time. Without this insight, we could measure distances and intervals, but we wouldn't understand the underlying structure linking them. This realization transforms our understanding of light. Photons travel at c because they are massless, but c itself is a fundamental property of spacetime. Even if photons had a tiny mass, the speed limit imposed by c would remain. Light doesn't determine the speed of causality, it merely obeys it. This subtlety highlights the elegance of the universe. The speed of light is baked into the very geometry of reality. It is both a physical and conceptual cornerstone, shaping how matter, energy, and information interact. Now, consider energy differences across the spectrum. Radio waves are low energy, stretching over kilometers, capable of traveling long distances with little interaction with matter. Microwaves, infrared, and visible light increase in energy, interacting more readily with atoms and molecules. X-rays and gamma rays carry enough energy to penetrate tissues, disrupt chemical bonds, and even affect atomic nuclei. Yet across all these variations, the photons obey the same laws, traveling at sea in a vacuum, displaying both wave and particle characteristics. They are united, despite their diversity, under the same quantum rules and the same speed limit. The practical implications are enormous. Every device that uses electromagnetic radiation, radios, microwaves, lasers, medical imaging, is harnessing the same fundamental particle, the photon. We manipulate its frequency, energy, and wavelength to extract information, deliver energy, or probe matter. From the cosmic scale of starlight traveling millions of light years to the everyday scale of a Wi-Fi signal bouncing around your room, light operates according to the same immutable rules. And here's a humbling thought. The light reaching your eyes from distant stars carries a record of the past. Every photon is a time capsule. The photons from Betelgeuse, for example, have been traveling for 700 years before reaching Earth. We see the star as it was centuries ago, not as it is today. Light is, in a very real sense, a chronicle of the universe, delivering information across space and time, connecting us to events long gone, long before we were ever here to witness them. This is what makes studying light so profoundly poetic. It's not just about particles and waves or wavelengths and frequencies. It's about understanding the threads connecting all things in the cosmos. Every photon is a storyteller, every wave a messenger, and every quantum fluctuation a key to unraveling the deepest laws of reality. Light is simultaneously simple and infinitely complex, ordinary and extraordinary, tangible and yet profoundly mysterious. Now, let's bring everything full circle and consider what light truly is, beyond experiments, equations, and measurements. Light is not simply a wave, not simply a particle. It is a bridge across spacetime, a thread connecting events separated by vast distances and eons of time. Every photon traveling from a distant star, a galaxy, or even the sun to your eyes does so without experiencing a single moment of time. From its perspective, the journey doesn't exist. The beginning and end are one and the same. This is both counterintuitive and breathtaking. Think about it. When you look at the stars, you are literally seeing the past. Betelgeuse shines its photons across 700 years of space and time. The light from the Andromeda galaxy has been traveling for 2.5 million years. Yet each photon experienced zero time in transit. The sun's light, reaching you in 8 minutes, was an instant for the photons themselves. They are cosmic messengers, carrying information from distant points in space and time, connecting the universe in ways that defy ordinary human intuition. This is where the poetry of physics shines through. Light doesn't merely illuminate objects. It links events, creates causality, and provides a bridge between classical and quantum worlds. It carries the story of atoms, stars, and galaxies. It obeys the fundamental laws of quantum mechanics while respecting the cosmic speed limit dictated by relativity. It is entangled, superposed, absorbed, emitted, and yet remains fundamentally the same entity across the spectrum, from the longest radio waves to the shortest gamma rays. Every photon embodies wave-particle duality, yet this duality isn't a limitation, it's a revelation. It reminds us that our everyday intuition about objects, motion, and time is not universal. Nature operates according to its own rules, and light is a perfect example of this truth. One photon can interfere with itself, become entangled with another across galaxies, and carry energy and information without experiencing any passage of time. The universe has encoded the deepest principles of reality within these tiny packets of energy, and we are lucky enough to observe them. Light is also a teacher. It shows us that speed, distance, and time are not absolute. They depend on the observer and the frame of reference. It teaches us that information has limits, the speed of light, but that connections, correlations, and patterns can exist instantaneously, as quantum mechanics demonstrates. Light connects the microscopic world of photons and atoms to the grand scale of galaxies and cosmic history. It links the birth of stars to the evolution of life, all through the subtle flow of energy and information. And perhaps the most humbling aspect is that we are intimately connected to this cosmic phenomenon. Every time you switch on a lamp, every time you see the sunlight glinting off a window, you are interacting with the same fundamental forces that govern the birth of stars, the formation of galaxies, and the structure of the universe itself. The photons striking your eyes have traveled through time, space, and interactions with countless particles, and they carry with them the story of the cosmos. This is what makes light not just a scientific concept, but a philosophical and poetic one. It's a bridge across epochs, a messenger of the past, a connector of distant events, and a unifying principle of physics. Light is what allows us to understand the universe, to probe its secrets, and to marvel at its beauty. It is simultaneously ordinary and extraordinary, found in a rainbow, a candle flame, a star, but operating according to laws that are deeply, fundamentally alien to our everyday experience. So, next time you look at the sun, the stars, or even a simple beam of light in your room, remember what you are witnessing: the ultimate connection between space, time, matter, and energy. Every photon is a thread in the vast tapestry of spacetime, linking the cosmos to your own eyes, the past to the present, the smallest quantum event to the largest cosmic structure. Light doesn't move in the way we think. It exists at the intersection of reality itself, a bridge, a messenger, and a marvel of the universe. After decades of study, thousands of experiments, and countless theoretical breakthroughs, light still holds mysteries that baffle even the greatest minds. But it also reveals one of the most profound truths about the universe. Everything is connected. Through light, we glimpse the structure of spacetime, the dance of photons and atoms, and the continuity of cosmic history. It is more than physics. It is the glue that binds the universe and our understanding of it together. And that, ultimately, is why studying light is one of the most exhilarating endeavors in science. It challenges our intuitions, stretches our imagination, and reminds us that the universe is far stranger and far more beautiful than anything we can easily comprehend. Light doesn't just illuminate, it connects, it informs, and it inspires. And now, whenever you look at the sky, a rainbow, or even the light streaming through your window, you can think about those photons, those time-traveling messengers, carrying the story of the universe and experiencing not a single second of the journey. That is the real magic of light.